My name is Hoiver. I'm with the binary technology team in PPRC, and I'm honored to present Chris Lattner here. I've been following the progress of LLVM through the years, and last March is the only first time I've seen Chris in action. So with so much adrenaline pumping and passion for the technology, I think we've got to do something about it, and here he is interning with us. So anyway, without further ado, this is Chris Lattner talking about LLVM with us. Thank you, Chris. Thank you.
So is this going? Yeah. So, like I said, my name is Chris. I'm going to be talking about a lot of stuff that I've done over the last few years. I'm hoping to make this somewhat interactive, and so if you have questions or comments, I'd love to get feedback throughout the talk. If you think I'm a fool, tell me, and I'll try to rebut it, and if not, I'll leave crying. It's all good. So this is work I've done with my advisor, Vikram Madve, at University of Illinois. So the big picture that you want to take away from the rest of this talk is that LLVM is a compiler and an intermediate representation. And the funny thing about LLVM is that it's a low-level representation that you can do high-level things with. And so it's low-level, which is good for making it efficient to operate on, simple to transform, easy to understand. But you can do high-level things like dependence analysis-based stuff, like recursive data structure reordering stuff, that makes it suitable for hosting a wide range of different kind of technologies. And this talk is going to be broken up into a few different pieces. The first one is going to be talking about the lifelong code optimization stuff that I presented at CGO. And this is to give you an overview of what the IR looks like, how it fits together into a compiler, and what the big picture kind of thing is. To explain how it works to end users that are working with it, I'll spend just a little bit of time talking about it as a compiler infrastructure, and this is how the software works. After that, I'll talk about two applications of the technology, one of which is high-level optimizations, recursive data structure, transformations, and analyses, and another is a very, very low-level thing, if I get time to it, which I probably won't, but which is looking at microarchitecture research and interesting ways to design processors for performance and future-proofing them. That kind of stuff. So I'll start out with the lifelong program optimization component of this talk. And so the basic idea of this work is to look at optimizing programs across their lifetime. So the idea is to be able to do analysis and optimization at static compile time, where it's cheapest to do these, at link time, where you get more information, you have a broader scope to analyze and optimize across, install time, where you have information about the end user's hardware, what they're using, so you can customize to that. At runtime, when you start getting information about how the end user is actually using the program, how they're, what's important to them, and at idle time, you can't do everything at runtime. Some analyses and transformations are too expensive, and so if you have a neat little screensaver that runs, you can do aggressive transformations and not get in the way of the critical path. Throughout all this, the key is that we want to be able to do high-level transformations. And so we want to be able to do aggressive stuff, as well as the lower-level kinds of things. And I'll talk about that, the distinction and what's important with that later. And I've talked about how we want profile information and this kind of stuff. Now, the constraints for this are pretty tight. We're looking at integrating with existing systems. And so we don't want to have the software developers have to change all their processes to do this. And so, in particular, if you're working as a C compiler, you don't want to have to change all your makefiles to use your system. You just want to say cc equals LLVM GCC and just have it work. Additionally, we want to support multiple source languages. We want to integrate with legacy systems. You don't have to recompile the world to work with this kind of thing. You should be able to use native libraries and stuff. And so this is kind of the goals of the work. Now, when we talked about this, we decided that there are 5 key things that we really need. So first of all, we need to have a rich code representation. It needs to be persistent. And so it needs to be rich, which allows us to do the aggressive optimizations and analyses that we want to do. If it's not rich enough, then what we'll be able to do will be so limited that it's not particularly useful. Persistent means that it has to be, you have to have access to the code at all these different points in the program's lifetime. And so you need, at runtime, you want to have the same representation for the program as at compile time. And that's tricky in a lot of compilers. We also want to be able to support offline native code generation. We don't want to have to JIT everything. Like I said, we want to do profiling and optimization in the field. We want language independence. We don't want to be stapled down to a particular runtime or object model, certain set of language exceptions, exception semantics for a particular language, things like that. We want to be as language independent as possible. And we want to be uniform across the whole program. So even if you have DLLs written in multiple languages, even if you have a just-in-time compiler that's running part of your application, we want to be able to optimize across these boundaries and analyze across these boundaries without having to write lots of stubs or other kind of ad hoc things. So we looked at existing work, and there's a ton of it out there. And across the top are the 5 different things I just talked about. There's different approaches. The one that comes closest is actually machine code optimization. And so if you look at machine code, you can optimize, across shared object DLL boundaries. You can, it doesn't have a runtime system that gets in the way. You can do end-user profiling on it. It has all the capabilities we need. You don't have to do offline code generation because it is code. The one thing that it doesn't really have is the ability to do high-level transformations. And, you can do basic block layout, and that pays off a lot. But you can't do dependence analysis-based loop transformations. You can't reorder data structures and do other high-level stuff. Just really not feasible on machine code. I'll talk about high-level virtual machines in a little bit, but as you're probably guessing, LLVM can do all of these. And so I'll talk about how that works. Does this make sense to people? And so, yeah. LLVM stands for low-level virtual machine. And so the IR, the code representation, is a low-level representation, which is basically a virtual machine. Virtual in the sense that it's like a machine code, not that it has a runtime and stuff like that. And so it's a virtual assembly language or a virtual machine. So what is our approach? Well, what we're going to do is we're going to take the best features of assembly language, that it's low level and that it applies to all source languages, and try to fix the one little problem with it. You can't do the high level analysis and transformation. And so what we did was we took a low level language independent RISC-like instruction set, a lot of 3-address code. We happen to use SSA for the registers, but because we're using a low level representation, it's language neutral, just like machine code is. We allow offline runtime native code generation as an implementation detail, but the important thing is that we have type information built in the IR. And so in particular, LLVM includes a low-level language-independent type system that allows you to express the important details that you need to do dependence analysis, that you need to do pointer analysis, that you need to do the high-level transformations that are typically done at the source level. Okay.
Question.
Yeah.
Other than types, what other high-level information do you retain?
Which part of the types?
Other than types, what other language type of information
Not
do you
much.
retain?
And so in particular, we don't keep class hierarchies or any.
So do you retain the orderability semantics of C expressions?
No. You serialize that. So the question is, do you maintain the reorderability semantics of C? Like, if you have a function call with arguments, for example, if there's not a sequence point in between the arguments, you can execute them in any order. So
Right, so there's no dependencies there.
Yeah, so we don't keep track of that. And so the C compiler would serialize that in some order, left to right, or whatever it chooses to do. And then we just respect the semantics from there. So there's a certain amount of high-level information that we don't keep, and a lot of source-level information we just don't have. But we can still do a lot of the same kinds of things on the low-level representation that you can do on a high-level one. So the specific contributions of this work are that we have some features for language independence, and we're the first to support all 5 features. Yeah.
Keep the alias information?
So we don't currently. In the future, we might. So things like the restrict keyword and Fortran argument, non-aliasing semantics, stuff like that. Is that what you mean?
Yeah, lots of
type-based alias.
whole body of code. Yeah.
We don't keep a lot of the source-level alias information like that. We do have extensive alias analysis, just interprocedural alias analysis and stuff like that, based on data flow. But we don't currently keep that information. In the future, we'll probably extend it to support that. Yeah.
When you say type information, do you mean sometimes rich type structure like arbitrary typing on?
No. So I'll talk about the type system in a minute, but we're not talking about classes and hierarchies and things like that. We're talking about arrays, structures, pointers. And in particular, the type system is immutable across all the source languages. And so you have a type system. It's low level, it's simple, and then the source level compiler compiles down to that. Just like it lowers the code, it lowers the types. So that's the idea. So you're probably wondering, why don't we just use the CLR to do this? Well, it really boils down to there being different goals, primarily. So in a high-level virtual machine, you have concepts like a class, you have concepts like a method call, or these high-level kinds of things. In LLVM, you have low-level concepts. You have loads, you have stores, you have adds, you have a function call. You don't have the high-level concepts. All of this stuff gets lowered down, and the optimizers and everything work on the representation at that level. So this has a few implications that are important. First is that if you ignore unverifiable CLI, you can't really do language-independent work. Right? You're restricted to use a particular object model. You're restricted to use a particular set of exception semantics in a runtime. Right?
What is verifiable CLI?
Or verifiable code, verifiable managed code. So, like the common language runtime, if you take a C# application, for example, or you compile to MSIL, is that what you mean? So basically,
You don't use C# on safe.
yeah. Yeah. So exactly. If it's type safe and so also you can't optimize the virtual machine code into the application very well. High-level virtual machines require specific runtimes. They're in a high-level virtual machine, you'll have like a load string constant instruction, and so that implies that you have a string class with a certain set of semantics. And CLI or the CLR isn't really used for optimizations directly. There's some work to do that, but you can't really support a full spectrum of optimizations directly on CLR code itself. There's a lot of things that you can't do, for example, eliminating bounds checks without reverting to unmanaged or unverifiable or other kinds of things.
Short of compiling LLVM into direct machine code, why wouldn't LLVM as well require a runtime environment to execute?
Okay, so that's a good question. So LLVM doesn't have any kind of built-in language runtime. So it doesn't have a class library. It doesn't have it doesn't have bounds checks, for example, and it doesn't have a lot of things that traditionally get packaged with the virtual machine. It doesn't have a garbage collector required, things like that. And so when you take something like MSIL and compile it down to LLVM, which is my summer project, incidentally, what you end up doing is you end up compiling the class library also to LLVM. And you take a garbage collector, and the LLVM code calls into the garbage collector. And so all these features are not part of the LLVM layer. They're just libraries that are implemented in terms of LLVM just like anything else. And this means that you just take your program, link it all together, execute it, and it just runs. Does that answer the question? So it's a virtual machine in that it's a virtual instruction set or a virtual assembly language, not a virtual machine in the sense that it's a garbage collector with a runtime and with a particular set of capabilities. And so, so like I said, you can take a high-level virtual machine, you can take a program in MSIL and compile it to LLVM. It's being worked on. So I've been really vague about what the IR actually is, so I need to talk about that. Basically, like I said before, it's a simple RISC-like instruction set. And so you have, three address code instructions like add. It works just like you'd expect. The registers are an SSA form. It's just a way of doing efficient data flow analysis. There are low-level control flow operators like conditional branches, stack unwinding, things like that. You don't have things like loops or ifs or source-level type of constructs. And all memory is accessed with load and store instructions, and all loads and stores have type pointers. And so here, this is just a simple example of something that's walking through an array, and it's calling sum on each element and incrementing some stuff, and it's not anything particularly exciting or particularly unusual. The more interesting part is that it exposes the high-level information that I talked about. And so the SSA form, because you have SSA throughout, whenever you have an LLVM, you have explicit data flow that's available. And SSA makes a lot of algorithms more precise and more efficient. You have an explicit control flow graph even for exceptions, which is kind of like Phoenix. You have language-independent type information, which I'm going to talk about next. But the key thing to think about here is that all the operands to everything are typed. And these types are a language-independent type system. So I don't have a ton of information about this here, but if you're interested, I can tell you more. You can ask me about it offline. But the basic idea is that the type system is this one slide. It's very simple. There's some number of primitive types like integers, floating point. There's a Boolean type and a void type for function returns. But beyond that, there's not really much else. There are 4 derived types. There's an array, a pointer, a structure, and a function type. So everything else is built out of these. It's just a composable type system. It's very, very simple. If you're a source language compiler, you have to do lowering. A trivial example is that a C++ reference turns into a pointer, and then any accesses through the reference that would be implicit loads and stores are turned into explicit loads and stores in the LLVM level. More interesting is that if you have class hierarchies, you turn them into containment with structures. If you have bit fields, those get lowered down to integers. I mean, all this kind of stuff gets lowered down and distilled into a very, very simple type system. And the type system is important because it gives you the information you need to do the analysis and the transformations. The structure fields give you the ability to do field-sensitive analysis, to look at how records are being used. The arrays give you the ability to do data flow on array elements, to do dependence analysis, to do loop transformations, things like that. Did you have a question?
Do you distinguish between managed and unmanaged pointers?
Nope, not at all. And so he asked if you distinguish between managed and unmanaged pointers. And so I don't really talk about how I handle like the garbage collector and stuff, but I could do that offline if you want, talk about that. But the basic deal is that, with managed and unmanaged pointers, you have, for example, inner pointers, and you have normal pointers to objects. Well, inner pointers are represented with 2 pointers, one of which is to the base object, one of which is to the field or whatever you're pointing to. Those get reported to the garbage collector. The garbage collector knows about them. It can walk the stack. It can find the roots. I mean, there's nothing particularly unusual. But at the LLVM level, they all just look like pointers. And one of the interesting things about LLVM is that if your source language is type state, and assuming your compiler or front end isn't doing silly things, the LLVM will also be, the LLVM will be target independent. And so you can take, an MSIL program, compile it to LLVM, then run it on any platform, regardless of the endianness or the pointer sizes or things like that. So part of what this entails is that there's this magic get element pointer instruction, which I should have added a slide about. But this get element pointer instruction is the key feature that allows us to do type-safe pointer arithmetic. The 2 things it does is it allows you to index into arrays and makes that explicit. So we don't have explicit address arithmetic exposed. And it allows you to index into structure elements. And these are 2 very, very simple concepts. But as it turns out, that's all you need to do. That's all you really need to do a lot of high-level work.
How do you represent constants?
How do we represent constants?
Which implies how many bits you have in a float.
There can be constants of different types. There's different size integers, for example. What specifically do you mean?
Okay. Is this textual or is it binary representation?
It's both. And so LLVM is actually a first-class language, and it has 3 different representations. It has an in-memory compiler IR representation, has a text representation like this, and it has a compressed binary representation. And one of the big features of it is that all 3 are exactly equivalent, both in terms of the structures that they contain and in how they work and how the structures are the same. This is good if you're working on a compiler pass because you can take the LLVM code, look at it, run it through your pass, look at it again, and see what happened. But it's also good because it makes it less enticing to add random stuff to the IR, which is a good thing. Does that answer your question? Or So I mean, the answer is that you have different size constants depending on the types. So if you have a 32-bit integer, then
When you say float, you have to decide how many bits you have, right? Because how do you put
yeah. So
it's not open, so you have to decide.
yeah, the float is a 32-bit floating point IEEE number. The double type is perhaps poorly named, but a 64-bit floating point type. So yeah, it's similar to MSIL in that way. How there's a certain number of set types, primitive types. Does that make sense? So the other thing is that you can do arbitrary pointer casts, and so this is important for languages like C, and this allows you to do horrible things like represent unions, which we don't have an explicit union type. Unions are lowered down to you have a memory object, and if you want to access it as one type, you do so, and then if you want to access it as another, you cast a pointer and then access it as that type. Very simple. It's important to be able to do type safety, but this implies that LLVM itself is not verifiable or secure or any of those things. And so, in particular, when you have a source language front end for a type safe or verifiable language like MSIL, what happens is the bounds checks and the different safety checks become explicit in the LLVM representation. And because they're explicit, they can be optimized away. That's the idea. So that's the really brief tour of the instruction set. And the idea was really to get you the idea that it's very simple in low level. That's basically it. Later I'll talk about, yes, it can do high level stuff, but for now it's simple and low level. The question then is, how do you build a compiler out of this that allows you to do lifelong code optimization? Well, the big strange thing that we're doing here is we're looking almost exactly like a normal compiler in a lot of ways. We have source language front ends that compile your source code, but instead of compiling it to native executables or .o files, we compile it to LLVM files. At link time, these LLVM files are brought together by the linker and linked together in LLVM. Well, since at both stages the code is in LLVM form, you can run any LLVM optimizations you want on them. And in fact, our link time and static optimizers share a lot of compiler passes. And we run interprocedural constant propagation in the static compiler, and because there's lots of simple cases that you can use just with local scope, for example. The question then is, how do you execute this thing? So at the developer side, we look just like a normal compiler. You compile each source file to an O file. This happens to be an LLVM O file. You link them all together. You get an LLVM executable. When you ship it to the end user, there's multiple different ways you can execute it. The simplest is that you can just JIT the code, dynamically translate it. You can pull in whatever shared objects you want. You can pull in whatever native libraries or whatever you need. Another way to do it is you can use static code generation. So at install time, you can run an ahead-of-time translator and compile it down. This is nothing unusual. The big thing that's important here, though, is that we keep the LLVM code with the native program. And so even when we compile to a native Pentium 4 executable, we have the LLVM code around. And so if the user did something silly like upgrade their computer or something, we could dynamically recompile the code or re-optimize the code. More importantly, when we're compiling it, we can also put instrumentation into the program. And so this instrumentation produces profile information, and then this profile information can be used to drive a runtime optimizer. And so you can do simple runtime optimizations, try to improve performance, whatever you want. Now, the important part about this is that the runtime optimizer has both the LLVM code and the profile information to work from. And so it can use standard profile-driven optimizations, and presumably just ones that make sense at runtime. If there are profile-driven optimizations that don't make sense at runtime, well, then you save the profile information somewhere, and like I said, you have a fancy screensaver that displays some cute graphics while it's re-optimizing the program. You can use standard profile-driven optimizations this way based on the end-user profile information instead of the scenarios that we typically use. This is all pretty simple and straightforward. The key thing that makes it work is the fact that the LLVM code allows you to do the optimizations that we need to do, and yet still retain the high-level information to do the high-level and the low-level optimizations. Yeah.
When you say you collect compiled information, do you intend to say that you will have anything other than the call graph?
Yeah. So do we collect anything other than call graph profile? So, I mean, we can collect different forms of profile information. Currently, we can collect, edge profiles, block profiles, path profiles, stuff like that. And so, I mean, currently our group is working on a path profile-driven trace reoptimization framework, for example. And so, the idea is that it's kind of a modular system, and you can, put pieces together how you need to. So it's easy to add different types of profile information. It's easy to write different clients that use them in different ways. Make sense? Okay. So, like I said, this provides all 5 different capabilities. The first is that, we have this persistent code representation, which I'll argue for a little bit more later. And so, since it's rich enough, which you just have to take my word for right now, these LLVM optimizations can be run at any time. And the big feature here is that we're not lowering the code as it goes through the compiler. That's effectively, when you distill everything down, that's what it amounts to. And so, because you're not lowering the code, because it stays in the same IR, optimizations you do at static compile time, you can also do at link time, you can do at runtime, you can do throughout the lifetime of the program. We support offline native code gen, we support profiling, language independent, just like a microprocessor is. One thing that people get concerned about is that we're not trying to be a universal IR in the traditional sense. We're not trying to be a union of all different programming language features. Instead, we're kind of the intersection of all different programming language features. We're trying to be minimal and support languages that way. And you can compile across any boundaries. You can compile and optimize and analyze across anything that you can compile to LLVM, which we think is anything. So, yeah, back there.
So I wanted to ask you something about you. You said you lower early and you never need to have a higher level form. So how do you deal with bid fields? Bid fields are lowered down into their, composite load store shift map type of stuff.
Exactly.
How do you represent that as a logical variable? How do you do constant propagation?
They're not represented as logical variables.
So there's a lot of optimizations you can do on that, right?
No, it's just that the optimizations take different forms. And so constant propagation through bit fields isn't the same as constant propagation through instance variables, for example. It just, things would have to be aware of the shifting and masking and stuff. I mean, it makes some things look slightly more complicated, basically, is what it amounts to. But on the other hand, all the optimizers and all the analysis overall is much simpler because there's dramatically fewer cases to handle. And so that's the trade-off, is that the language is very, very simple. I mean, you saw that, which is good for the optimizations and the analysis. You can ask, well, what does this code look like? Okay, we'll compile it with the front end, see what it generates. That's exactly the IR that your transformation will have to deal with. There's nothing hidden. There's nothing that's in the memory IR that's not in the assembly language dump, for example. And because it's simple, it's easy for people to learn how to use it. Because it's simple, there's certain things that are more complicated, but you can still do them. So, yeah. Yes.
So, I'm not a points-to analysis expert, but in the algorithms I've seen, they often have type information, like when you're doing downcasts, that narrows your points-to sets. And if you're throwing away some of this high-level type information, how does that?
So you're talking about rapid type analysis or class hierarchy analysis, stuff like that?
Things like that.
We don't have any good way of dealing with that right now. In the future, we're probably going to add a simple mechanism for expressing a safe pointer cast. And so if you know, due to language semantics, that a cast from one pointer type to a base type, for example, is safe, the source language will be able to express that directly.
Well, I mean, just like when you're doing a downcast, like in a managed safe language, if that cast is not correct,
if it fails, you'll get exactly.
At that point, the points to your point
That's
not proper.
Yeah.
So if you're doing points to analysis, your points to set will narrow.
Absolutely. So that's what I'm talking about. Is what we're going to add in the next whenever somebody gets around and feels like doing it, is an instruction that's a safe cast. It takes a pointer, and it produces a pointer. And the semantics are that if the destination pointer type are not compatible with the source pointer type, the results are undefined. Now what that means is that the source language front end has to guarantee that that's true. And so in an MSIL front end, you'd produce the code to check the cast as normal. If the types don't agree, then it throws the exception, and the safe cast would not be reached. What this means is that the analysis can now look at this and see that you're casting from one to the other. It exposes more directly the flow.
Static analysis using the type information. Right? So throw away the higher level type information.
Okay, so one of the funny things about this is that a lot of type information doesn't really mean anything. Source level type information doesn't mean anything at the LLVM level. What means things are pointers to vtables. And so what you're really asking for is when I call this method, this virtual method, I'm loading a pointer out of a vtable.
You have an equivalent representation. Essentially, there's a mapping between. If I had a class hierarchy, there's essentially a mapping to that.
Yeah. So when you compile a language like C#, you have a class hierarchy. You have virtual methods that are overloaded. Well, each of these classes gets a vtable, turns into a global variable in LLVM, right? And so what happens is you have an object, you load out the vtable pointer, you load an element out of that vtable, dereference it, call through it. The question is, what does that dereference point to? Right? If you can resolve what it points to, you can turn the indirect call into a direct call. And so the question is what is that vtable pointing to? And so it turns into, I can talk about this later if you want.
If you throw away that type information, the hierarchical class hierarchy information, there are potential optimizations that you could do in runtime. Perhaps using the type information that you have at the source code level that you could do in the runtime.
Yes.
Now, won't be able to do once you throw away that information.
Yeah,
So,
absolutely. The goal of LLVM is not to preserve all the source level information. That's an anti-goal.
I understand.
There are things that we definitely cannot do,
Yes.
right? Or things that are uncomfortable to do. Right? We're working on adding a general mechanism for keeping source level information around. But the problem with that is that anything that uses that source level information is tied to that source language, right? So if you're doing rapid class hierarchy analysis kinds of things, you're tied to languages that use class hierarchies, and probably in a particular form, right? It's not going to work on OCaml programs, for example. So far we've been focusing on the common subset, or the common optimizations that apply to a broad range of things. Now, in practice, simple pointer analysis algorithms, standard pointer analysis algorithms can do a lot of indirect function call resolutions and can do a lot of the things that people do with simpler means. And it's a trade-off. This is what we've chosen. We're looking at adding more to it. LLVM isn't a static thing. So.
Before the LLVM.
So that's definitely possible. And so what I'm getting to next, sort of, is the idea that LLVM is really a system built out of libraries. Okay. And building a tool or building a system is all about putting libraries in. And so you can imagine you have a Java front end, which we have a person working on. This Java front end translates a class file at a time. Okay. Well, you can run that statically, or you could run that just in time. So in the just in time setting, you can be parsing the Java class file, converting it to LLVM, doing whatever optimizations you want, outputting native code. In the source level, you can do any source level optimization you want. And so, just like now with LLVM, the source language could add any information it wants to the LLVM files, which at link time you could write a language-specific optimizer, which reads that information and then does things. That's easy. It's just that we haven't focused on that yet.
So is there a reason that you use a lower level language like LLVM instead of MSIL just for language independence, or is it easier to do optimizations in LLVM?
I would claim that it's easier to do optimizations on LLVM. However, I've never written an MSIL optimization, so I obviously have an uneducated and biased view. The nice thing about LLVM is that it's very simple. It's explicit everything. It's all there. MSIL is a little bit harder to deal with directly because it's stack-based, for example. And so what that means is that in practice, all MSIL compilers, first thing they do is get rid of the stack. Then you don't have MSIL anymore. And so you do some stuff, and then you convert back, add the stack back, if you're going back to MSIL. In LLVM, you read in the text file, that's exactly what you have. You do some stuff, you write it out exactly as you have it. It's very efficient that way. There's definitely benefits to doing it. There are definitely benefits to doing it on MSIL. One of the big things with MSIL is you're limited to what you can compile to MSIL.
I didn't see this, but do you have something that's equivalent to volatile?
Yes, yeah, definitely. We do have volatile. And so for handling threads and memory safety stuff.
How does this intermediate language affects compile time? Does it doubles it, triples it?
So how does it affect compile time? Do you mean the link time optimizer, or do you mean comparing against?
I mean the whole cycle from compiling my program to generating the machine code.
Well, so how does it affect it compared to what? Compared to a simple static compiler?
Compared to current compilers, tuple-based, or compared to...
So there's no implicit inefficiency due to the system, basically.
But it should be, right? Because you're basically generating intermediate language, which you should optimize as well, right? So it's kind of additional step.
Well, so all compilers usually use an intermediate representation.
Yes, but they're not optimizing this intermediate representation. So what you're saying, you basically...
That's what compilers use intermediate representations for. So, a traditional, a static source-level compiler usually parses the source code into an AST or high-level representation.
Yeah, I know that.
Converts it to a mid-level representation to do optimizations on. And then converts it to machine code.
Yes, but it does not convert it to different language, like you suggesting. For example, you are transferring the code to some simplified RISC type set of instructions, right? Which is basically another. It's much more difficult task than just represent.
Well, you're right in the sense that it is a full-fledged language, right? But it's not any more difficult than lowering it to any other IR. If you have, say you have a plus operation, your C99 front end, an integer plus turns into an LLVM add, a complex plus turns into a little bit of a few additions. It's not a big semantic gap. It's not like a stack machine, or I don't know. I've written several front ends and they're pretty natural.
So do you have any numbers comparing between the size of the LLVM if you
and
talk about
native machine code? Yeah, I do.
But we can get to it.
I don't remember if they're in my backup slides or not. That's the thing. I'll just tell you. It's easier than finding it. The basic point is that the LLVM compressed binary form, before you run gzip on it, is about the same size as x86 machine code. It's about 30% smaller than Spark machine code, something like that. If you run gzip on it, it's half that. Oh. I did not have a mouse here. I found it. Okay. So it's not big, basically. And there's room to make it smaller. We haven't done a whole lot with that, but basically it amounts to being a simple RISC-like instruction set. And so most instructions in the IR turn into a 32-bit word in the machine code, in the byte code format.
Okay, so in memory or static?
In memory, I don't have any numbers for you, but it's pretty small. We can compile and optimize 100,000 lines of code programs in 100 megabytes or something. It's
One of the issues when you were doing the global optimization, when you bring in some of the shared library and LLVM and other stuff.
Yeah, not so far. We haven't dealt with 10 million lines of code programs yet, so I suspect that there's things you can do. Now, there's features in it, so you can incrementally load functions, incrementally deserialize functions out of the bytecode files, and do smart things to not keep everything in memory. And so if you're doing your interprocedural analysis, you can bring functions in from disk, do the analysis, push them back out. I mean, simple things like that. And so we haven't done any of that, but it's all implemented, and the JIT, for example, incrementally pulls stuff in. So I don't see there being any major problem with that. So, I mean, you can't, if you're dealing with 10 million lines of code today, you can't hold it all in memory. There's basically really no good way around that. And so you just have to be smarter about what to do. So I'm going to move on a little bit now and talk about LLVM as a compiler infrastructure. This is pretty quick. So like I mentioned before, one of the funny things about LLVM is that the actual tools have very little code in them. And so if you have a tool, it's not uncommon to have 30 lines of code. Well, the reason for that is because almost everything interesting lives in libraries. And so when you're building a tool out of LLVM, it's a matter of, pulling in the libraries you need, writing some glue code, and you're done. These libraries take, the form of what you'd expect. You can have language front ends, you can have compilers, you can have x86 target, you can have a just-in-time, the language-independent just-in-time stuff, profile guided stuff, whatever you need, you can just pull it in. This makes it easy to write and debug the different compiler parts. And so the nice thing about this is that you can, link these things as shared objects, which means that you can work on one component. You don't have to recompile the world to use it. There's lots of samples and stuff. One of the other neat things about LLVM is that we are an infrastructure, not a framework. And what that means, and the distinction that I like to give that, is that you can replace a component of LLVM, like a register allocator, an alias analysis, or a profile implementation, or whatever. You can add something to an existing compiler, or you can just replace a big component. You can replace the entire code generator. And that's really important because not everything is a register machine, for example, right? I mean, we have people using LLVM to compile to FPGAs, and our register allocator and scheduler and stuff don't really make any sense for them. So the big thing here is that the libraries that we provide with LLVM don't have any special status in the system. There's nothing that requires you to use them, and you can either link them in and reuse them for productivity reasons, or if you feel the need to, you can rewrite the world. Here's just a few simple ideas, and just to give you an idea of the library granularity kind of stuff. So we have simple tools like LLVM AS and DIS, which convert the text representation to the bytecode representation and back. This link program which links some bytecode files together. Opt is a modular optimizer. You just say, run this set of LLVM passes on this bytecode file, produces another one. Each of these tools is just, like I said, 30 lines of code or something. Just pulls in the libraries and pull in a bytecode reader, pull in the optimizations you want, and pull in the bytecode writer. That's all you need. LLC is a code generator. It's pretty simple. LLI is the execution engine we use, and that ties into JIT or interpreter if you don't have a JIT, stuff like that. So those are the primitive tools. The more interesting ones are, like, if you're building a C compiler, you need something more than just an assembler, and you don't want your users running opt this optimization followed by this optimization followed by this optimization. And so the C compiler uses these two tools, one that runs at compile time, one that runs at link time. They're pretty simple. At compile time, we just read in the .ll file, the text file produced by the C front end, by CC1, run a bunch of optimizations on it, and write out the bytecode file. At link time, we pull in the bytecode files, link in any libraries that are in LLVM form, resolve any .a file, any dependencies on A files, pull in bytecode files out of A files rather, run some more optimizations, and then write out a bytecode file, and optionally write out an executable. Really simple stuff. Again, these are just wrappers around the existing stuff we have. And so the big piece here, the big important thing is that if you want to build a compiler out of the infrastructure, you pick the pieces that make sense, you pick the domain-specific optimizations that make sense, you build the tool out of the pieces you need. It's pretty simple. So here's a more interesting tool, and it's an example of the kind of thing you can do with the modular system. We have this tool called BugPoint. So people never like compiler bugs because they're really difficult to track down and have really strange effects. And so we got tired of tracking down bugs, and so we decided to write a tool that did it for us. So the idea is very, very simple. The idea is you just, the standard way you debug a compiler problem is you say, okay, something goes in, something happens, something bad comes out. Let's change the something in the middle until we can narrow down what is the cause, the root cause of the problem, right? So what bug point does is it takes in, the input from your front end, completely unoptimized, takes in, the list of optimizations you're running and the code generator that you're using, and it basically says, okay, does the program work without any of the optimizations? If it works, then one of the optimizations must be doing something wrong. And if it doesn't work, then it must be a code generator problem, right? So if you have an optimizer problem, it then does a binary search, sort of, and narrows down the location of the problem in the set of passes. So it runs, all the optimizations but the last half. If that works, then it must be something in the last half, and it just kind of narrows it down until you get down to the pass or the combination of passes that you need to reproduce the problem. If you have a crash, for example, it's really easy to do this kind of thing because you just take the program. So after you know roughly where the problem is, you then want to narrow down the input test case, right? And because having 100,000 lines of C code into a big blob of LLVM doesn't really help you very much tracking down the problem. And so the tracking down a crash, it's pretty simple again. You throw away part of the program, you test it. If it fails, if you get a crash, then you narrow the program down, you keep going, you iterate until you get down to a small test case and you can't throw anything away. And so we throw out functions, and then we throw out basic blocks, we throw out instructions, and usually we get down to like the 3 instructions or the 2 basic blocks needed to reproduce the problem. You say, oh yeah, that's right, I don't handle irreducible regions, do I? Whoops. So it works really well in practice, and it's just a simple greedy algorithm. We don't try to do anything smart. The nice thing about it is that it's completely black box. We don't know anything about the optimizations in the code generator, and so we don't know it's a global optimization versus an interprocedural optimization. It works all the same, which is nice. Yeah.
Just a comment. I don't know if you're aware, but Andreas Zeller has done something like this called delta debugging.
Yeah. Yeah, it's related, and I'm not claiming that this is, amazing new research material. This is just kind of the effect of having a modular system, and it's something that's incredibly useful, and we use all the time. Debugging miscompilations is the same kind of thing, right? If you have an optimizer that's doing something bad, you just split the program in half and optimize half of it. If you have a code generator that's misbehaving, you split it in half, run half of it through the C backend, half of it through the x86 backend, link them together, and reduce the amount that you're sending through the the LLVM code generator. We can take out functions, and we take out loopness, and we take out individual basic blocks. It's pretty simple stuff, but it's nice, and it works. So one of the funny things about it is that if people are working on a new or kind of in development or beta thing, they'll run into a bug in some program, it'll crash in a certain place, they look into it, they run bug point on it, it finds a problem in something that's completely unrelated, because bug point doesn't know the particular problem it's chasing down, it just knows that it can reproduce a crash or it can reproduce a miscompilation. So you don't always find the bug that you thought you were going to find. But it's still a bug, so you should fix it.
You can only find crashes, right, through your bug point?
It can find miscompilations. And so with the miscompilations, it runs...
It's difficult to say, right, whether a particular output program is running correctly or incorrectly.
So you're right. Yeah, so what we do is we run the program, it produces some output, we diff it with known good or the program without optimizations, basically. And that has the obvious problem of if the program's not deterministic, then it's not going to work. So you either hack your program to be deterministic, or it would be easy to put in a shell script that ignores certain bits. I don't really know how well it would work with GUI applications, for example, because if you have a user in the picture, they get tired of clicking on the same series of things 1,000 times as trying different combinations. But for our purposes, it works pretty well. So, anyways.
Maybe there's a program which automatically clicks on the button.
I suspect somebody's done that. I suspect that Microsoft has tools that do that too. But so, as a compiler infrastructure, it's publicly available. You can download it. There are public releases. We have people outside our group that are contributing to it. Has a bunch of stuff. Has C and C++ front ends based on the GCC parser. Has backends. Has a bunch of optimizations, analysis, all that kind of stuff. People are working on new front ends. People outside the group are working on front ends for like Python and Ruby and Scheme and stuff like that. I mentioned the runtime optimizer, and there's lots of other things that are kind of just starting to take off and do stuff. C backend means that anything that you compile to LLVM can compile to C. And so, for example, we don't have an ARM native backend, but if you have an ARM C compiler, you can take your C++ program, compile it with LLVM, output C code, and then compile it with the ARM compiler, for example.
In view of compilers, I have a conditional question for you.
Okay.
How do you compare LLVM to, say, an intermediate conditional language for other compilers like GCC, like the RTL?
So compared to specific ones like RTL, RTL doesn't have any type information. It has similar flow information. The exceptions are implicit, and there's details. Other bigger problems with RTL is that it's target specific, and so a particular form of RTL, it depends on the target that you're compiling for, which makes it a nightmare to do anything with. Another big problem with RTL is that it's not an intermediate representation that's very well defined, and so it's kind of these memory structures plus a set of global variables plus a set of other stuff that all defines the state, plus the stuff that you've already output to the S file, which is implicitly kind of part of the IR. So LLVM is like it's a self-contained language, basically.
Backend.
Yes.
Once you have a C backend, you can use a standard compiler asking it not to do any optimizations and compile it to
Yeah, absolutely.
So what is the pros and cons?
So the problem with doing that, so he asked, if you already have a C backend, why bother writing native backends? First, writing native backends is fun, and there's a lot of interesting amount of work you can do. Also, the performance you get from the C backend isn't necessarily wonderful because the semantic gap between what LLVM can represent and what C can represent is big sometimes. So, for example, in C, you don't really have exception handling support. And so when you compile a C++ program to C, you get set jump and long jump all over the place. Right? So you get set jump long jump style exception handling, which is slow. Likewise, garbage collection support, C doesn't really have garbage collection support, and so you get emulated stack frames as part of the C code, which aren't as fast as having code-gen support for that. Everything works, it's just not necessarily blissfully efficient. Does that make sense? So if you're going for performance, you want to be able to, C doesn't have the ability to express certain constructs.
So how do you get target-specific concepts and optimizations into LLVM, like x86 addressing modes or predicated execution?
So the question is, how do you get target-specific optimizations or target-specific information? So there's a couple of different levels to that. So the first is, target-guided or target-affected optimizations. So things like strength reduction, or things like loop optimizations for cache hierarchies, where you need to know the size of the L2 cache. For that kind of thing, if you know, we have a target description framework, and you just say that, on the x86, it's cheap to multiply by 4, so don't bother strength reducing anything, just multiplying by 4. Or you can say the size of the L2 cache is 1. You can do that. For things that are really code generator specific, they end up in the code generator, and that happens as the last phase of LLVM. And so you can do that. You can run a code generator at link time, you can run it on the fly at runtime in the JIT, you can run it in stall time, whatever. But that's where you'd implement things like the addressing mode selection support. That's where you'd implement predicated execution support. LLVM has support for limited support for predicated execution in it. But
So when do the backends have their own? Once the code's in memory, the backends have their own internal representation.
Yeah. Yes. So they have their own code generator specific IR, but it's basically like an RTL level representation.
So given that, how do you do register allocation on LLVM?
You don't.
Is that always done in the in the back?
Yes, that's always done as part of the target. And so LLVM is an SSA form. And the way all of our targets so far work is the SSA form lives exactly until register allocation. The register allocator is the one that's in charge of getting rid of this infinite register abstraction and giving you your 6 registers that you really have, or whatever. Does that make sense? And so, but the idea is that you can do a lot of the optimizations that you traditionally do in a code generator on the LLVM. Not all, but a lot. And so that makes the code generation pretty quick in practice. So that's it. Yeah.
You mentioned that you don't have an AMD backend. Is it AMD compatible with x86?
I said not an AMD.
You said ARM.
Oh, I said ARM. But I mean, yeah, we don't have an AMD 64 backend yet. But I mean, adding it is obviously not that big of a deal. Beyond, I mean, it's not in particular harder to add a backend to LLVM than any other compiler.
How important is the choice of making the register-based IL description for stack-based machines? So if you have a stack-based native machine code that you have to translate to, how big would be the impact of choosing the IL that you have chosen?
I've never done that. So the question is since we have a register-based intermediate representation, what is the impact of converting it if the target is a stack-based machine? Is that what you're asking? So I have no idea. I've never done it. There are lots of people in this room that have done it with other compilers, so I mean they're well-known kind of algorithms for doing it. But I personally have not. Yeah, so he asked if we benchmarked it. So on C++ programs, I mean, we basically compare against GCC. We can basically beat it like 30% to 6 times, depending on the program, primarily because GCC doesn't really do C++ very well. C programs, we are, 10, 20% better in some cases, 10, 20% slower in other cases. A lot of it is just because we haven't spent time doing performance work, because it's much more interesting from the research perspective to be doing new things and implementing new capabilities. But I suspect that when I graduate, that might change. Okay. So that's kind of LLVM as the compiler, LLVM as the representation. LLVM, kind of told you how the whole compile process worked. Next, I'm going to talk about some applications of LLVM. And so the bigger, more interesting one for you guys is probably going to be the recursive data structure stuff. So I'm planning on spending more time there. If we have time to get to the microarchitectural research stuff for processor design, then that would be cool. But if not, oh well. So what are recursive data structures? Well, we all know they're like lists, they're binary trees, stuff like that. They're heavily used by lots of programs. Some programs don't use them at all, scientific programs. Other ones live and die by them. Problem with them is they don't perform very well with modern architectures. So when your memory latency is hundreds of cycles, if your recursive data structure is scattered all throughout memory, if you're chasing down it without much work on each dereference, things just don't work very well. And so they're an interesting target. They're also a hard target to deal with. So there's lots of approaches for dealing with this kind of a problem, and lots of people have worked on it. By far the most common, and historically the most common, is simple alias analysis-driven optimizations. Things like eliminating dead stores, eliminating redundant loads, moving things around, stuff like that. More recently, now that type-safe languages are becoming more popular and more available, we get into things like structure reordering, structure splitting, trying to take cold pieces of structures and putting them someplace other than where the hot pieces are, stuff like that. Other things are, if you have a runtime system like a malloc free library or a garbage collector, you can do things, you can implement heuristics to try to co-locate objects so that, in practice, though they could be scattered throughout memory, they're actually close together. And if things work out right, then you get a lot better performance out of it. So what I've been thinking about over the last few years is, can we do something more holistic or more systematic with data structures as a whole? Can we look at a recursive data structure and treat it like a loop nest optimizer. Can you devise a plan to deal with it to optimize it well? That's the kind of thing that I've been thinking about. But of course, this is a hard problem. And the hard problem is due to a few reasons. First of all, the analyses that are typically used, especially in commercial compilers, have a lot of constraints they have to work under. First, they have to work on real programs, have to deal with real-world problems like casting and other issues. They have to be efficient enough for people to use because users are going to be compiling the programs and you don't want them to wait forever. And because of these kinds of things, the algorithms used tend to be pretty restricted. And so in particular, most alias analyses, for example, treat an allocation site as a memory object. So if you have a constructor for a linked list node, if all of your linked lists nodes are allocated from that same spot, the alias analysis won't be able to distinguish if you have multiple different linked lists because they're all the same memory object. Okay. And if you go to something smarter and more aggressive, techniques like shape analysis, you suddenly get into the realm of doubly exponential algorithms, and they don't work if you don't have the entire program to deal with, and there are problems using them in a commercial setting, let's just say. Another very different problem is that even if you know everything about the data structure statically, you don't know anything about dynamically. You don't know where the memory objects are going to be at runtime. And traditionally a compiler has very little control over that. You can integrate with the runtime and integrate with the garbage collector or the malloc free library, for example, but there's few guarantees that can give to the compiler to make decisions. So for my work, I've been looking at something a little bit different. We're trying to analyze and transform entire data structures, like I said. This is composed of two major pieces with lots of follow-on stuff that I won't talk about today. The first piece is called data structure analysis. So in some ways it's just yet another pointer analysis, like people have been working on for years. But it combines a few interesting and new things together in a way that make it useful for this kind of application. And so in particular it's aggressive in that it can find a lot of interesting properties about data structures. It's scalable, it is very fast, and it works in the real world. So it works with type unsafe casts, incomplete programs, variable arguments, all that nasty stuff that you have in C programs. It identifies data structures and their properties, the important properties that we want to be able to do for analysis, we want to use for analysis and transformation. And if you're a pointer analysis person, it's a context-sensitive analysis, it's field-sensitive, and it's flow-insensitive. Okay. Once we have this analysis, then we use this transformation. So the analysis gives us static information about how the heap's being used in the program. To control how the heap's being used, then the compiler uses this transformation called automatic pool allocation. And the basic idea is to do what people have been doing for years now, is to take a program written using malloc and free and change it to use a custom allocator library. The important thing about this, though, is that since the compiler knows about this custom allocator library, it knows some of the semantics, and it can reason about where memory objects are at runtime, and it can do interesting things with that. So I'm going to talk a little bit about this. I'm not going to get too deep into the technical details of how the analysis works and how the transformation works, but I hope to get across the big picture, and if anybody has questions, please feel free to bug me whenever you want. I like talking about this stuff, strangely enough. So like I said before, it's context-sensitive, field-sensitive, and it's still scalable. For identifying data structures, the two big features that you need out of a pointer analysis are field sensitivity, the ability to distinguish between different elements of a record or structure type or instance variables in a class, and the ability to identify objects based on their allocation call path. And so, in particular, if you have a function that allocates a memory object and it's used to allocate memory for multiple different data structures, you want to be able to know that there are multiple different data structures. You don't want to merge them all together into one thing. So in order to be scalable, in order to be realistic, we made two compromises. So it's a unification-based algorithm, which means it's a Steensgaard's-like algorithm as opposed to an Anderson's-like algorithm. And it's flow insensitive, which means that we ignore control flow. In practice, these concessions aren't too bad because flow insensitivity isn't that much of a killer when you have SSA. You get a lot of flow sensitivity benefits just by using SSA. And unification actually works out pretty well for us because we want the data structures unified anyways. And since we're field sensitive, we don't get lots of spurious collapsing of objects due to fields that point to different types of things. So anyways, this is a fast algorithm. Despite the fact that it's pretty aggressive, on Pavre, which is Pavre with libpng and libz, it's like 8 seconds or something on Opinion 4, and it took 16 megabytes of memory or something like that. I have the numbers later. And the way it does that is that it's field sensitive and keeps track of type information, but it only does so for things that are type safe. And so if memory objects are not type safe, it gives up and it doesn't try to be field sensitive, which is part of it. So like I said, it works with C, which is hard. So what's new in this? Well, the basic new algorithmic feature that makes it work is that it keeps track of information it doesn't know. Or rather, it keeps track of what it doesn't know. That's a better way of saying it. And so for each memory object in the graphs that it builds, it keeps track of whether or not there could be information in that node that isn't represented in the graph yet. So you can imagine if you take a pointer and you pass it to some external function, that function will never be analyzed. You will never know what effect it has on the memory object. That function throughout the whole, or that memory object throughout the whole analysis will be marked as incomplete, or there's information in it that we don't know about yet. Basically is what it amounts to. Now, the important part about this is that it allows us to handle incomplete programs and some difficult things. It also lets us be speculatively field sensitive, which means that we can assume that we're field sensitive until we find a reason to think otherwise. And as long as the incomplete flag is set, we're still safe, conservatively correct. Other neat features are it incrementally walks the call graph and constructs the call graph on the fly without a previous pointer analysis. It walks the SECs of the call graph, which means that it doesn't have to iterate. It doesn't have to do a fixed point analysis, which is important for efficiency. It's, like I said, field sensitive for type-safe memory objects. And the key to being context sensitive with full cloning of memory objects and still being scalable is the unification. And so you can imagine that if you're naming memory objects based on the entire call path up to that memory object, up to that allocation site, well, you have an exponential number of objects in the program, and this is very slow. However, using the unification-based approach that Steensgaard popularized, most of those memory objects all get folded away, and it works really well in practice. So I'll try to give you a little bit more concrete details here about what we're looking at. So here's a simple program. So this program, calls a few functions. This one allocates the list on the heap. This one adds the contents of G to each element of it, and those ones free the list. Something simple. So the graph built as part of the analysis looks like this. It's pretty simple. It says that the X scalar points to this recursive thing, a Y scalar points to this recursive list thing, and there's also the global as a memory object as well. So the important part about this is it captures things that are useful for clients of the pointer analysis. So it captures the type information. Now the list that it captured isn't the shape analysis type of list. It doesn't know that it's a linked list. That's the program type list over there. And by capturing the type information, what it's done is it's shown that though in LLVM you can cast pointers around, you can do type unsafe stuff. it's verified that the code is actually accessing that memory object in a type-safe way. And within the scope, these memory objects are allocated, used, and destroyed. And so all the information, since we've analyzed these functions into this one, we know for sure that this is always correct. So the C flag on this thing basically means that it's complete. There's no incomplete information. It's not missing anything. And so a client could look at this and say, okay, well, this is used as a list object or a list type, and it's used in a type-safe way. And so I could do, for example, field reordering without horribly breaking the program due to type safety stuff.
What's HMRC, GMRC?
So the storage, so some of the other flags, so we keep track of the type of memory in each object. So G means global, H means heap, S means stack, U means unknown. Unknown memory comes from if you take like a random constant, the address of a device driver or something, and cast it to a pointer, you'll get an unknown object. M and R are mod and ref, which are not useful for this work. So the field information, because we know that the object is type safe, we can keep track of field sensitivity, and in this context that means that we can keep track of the distinction between the next pointer and the payload on the linked list, basically. And the most important thing for this work is the fact that we've proven that these two linked lists are disjoint. And it's fairly easy to see how that works. It's just hard to get it in practice. But basically it's because we've found that the memory allocated through this call site is different than the memory allocated through that call site. And that's part of the context sensitivity with cloning. And that's what it gives you. Okay, so, what's that? Somebody ask something? Okay. So, yeah, I'm not going to talk about how the algorithm itself works. I could spend an hour-long talk on that alone. But, here's some random programs. Lines of code, time to analyze, memory. The stuff on the right is the size of the graph. And so for the whole program, there's like 26,000 memory objects in the program, or nodes in all the graphs for all the functions in the program. And the biggest graph, which is a big SCC, has 167, basically. And if you plot this, that's my... Okay, so insightful content. So one of the interesting things about this is that though we're dealing with crafty C codes here, the majority of the programs are actually surprisingly type safe. And so if you look at, so this is looping over all the loads in the program, looking at the data structure graph that the load is pointing to, the pointer points to, and ask, was it type safe? Do we have field information for that load? And what we find out is that for a lot of programs, we get a lot of type information. Even in something like Vortex, which is not a particularly nice program to work with, you get a lot of type information. The ones where things start to fall off are where you have custom allocators. And so what happens is data structure analysis doesn't know that memory allocated by xmalloc will always be disjoint from each other. And so when it goes into the xmalloc call, for example, it sees that you're doing all this random pointer arithmetic and returning pointers to this buffer. And because it doesn't know that it's disjoint, it can't do any analysis based on that. And so because of that, everything gets collapsed together, it gets really ugly. You get...
If those allocators were annotated, do you think those percentages would be much
Yes.
higher?
If we knew that they were mallocs, this would be higher. And I have an experiment later in the pool allocation section that talks about that. But the basic point is that even though we have really crafty C programs, few are 100% type safe, but a lot are mostly.
Do you know what's going on with GAP? Because I don't think GAP has a custom allocator.
It has a new bag thing, or it does have a custom allocator. Some of these, I don't think Mesa does. I'm not sure. I don't remember offhand. Some of these are just due to the analysis not being particularly brilliant about something or other. I don't remember when I gathered these numbers either. So what happened to my? Well, that's silly. Well, anyways, I had a neat little chart or graph that showed how it scales, and it scales pretty much linearly or log n with the size of the program. So across, I have to have that somewhere. Let's keep slide. You know, I bet I have blank slides for a reason. Okay, well, you'll have to trust me on that. I guess it didn't come through in translation. But, so I've talked about this before. So the big thing that makes DSA work well is that it keeps track of incomplete information. And this has a lot of interesting effects. You can do field sensitivity really efficiently. The intermediate analysis, you can stop DSA at any point in the analysis and it's correct. It's conservatively correct. It uses this incomplete information to discover the call graph on the fly. It's field sensitive for type-safe memory objects. If you're doing something bad, it says, oh, that looks scary, I'm going to give up, and basically treats it as an array of bytes. And DSA is safe for C and C++. So more interesting than the analysis itself is the application of it, I think. And pool allocation is one of the major applications. I mean, it can be used for traditional pointer analysis stuff. I mean, we can plug it into modref type problems and scalar load and store type problems. But if you start using the advantages or the features that a cloning-based context-sensitive analysis gives you, you can do some interesting things. And the pool allocation was actually the motivating force for doing the DSA stuff. But so, what is pool allocation? Pool allocation historically has been something that programmers, C hackers, do to improve the performance of their code. Right? They spend a lot of time mallocating and freeing some memory, and it's not working so well. It's really slow, the locality sucks, they need to fix it. So they use, so in C++ you can use per-class allocators, in C you just write your own little package to do this kind of stuff. Pointer analysis people hate you for doing it, but it is effective and it works. So we're looking at doing fully automatic pool allocation. And the idea is really, really simple. The idea is that you take each heap node in the data structure graph that I showed you before and turn it into a pool of memory. Very simple. These pools are usually type homogeneous. So if the program has type homogeneous objects in this data structure, and if the analysis can know that, then they're type homogeneous. And in C programs, that's the case. And if the analysis is able to prove that it's disjoint, then they can go into separate pools. So that's the idea. So why even bother doing this? So the basic idea is, like I said really early on at the start of this talk, we don't want to look at individual loads and stores. You can get much better results if you look at the data structure as a whole. And to do that, you need static information about the memory objects in the program, but you also need dynamic control over where those objects go. And so the primary goal of this is to give the compiler that control. If you can tell it that all of the objects for this data structure live at this piece of memory, and at runtime, you can do follow-on transformations that use that property. You can do interesting things. In some cases, you can do simple shape analysis-based stuff. In very limited cases, often, which pools point to other pools, or garbage collection implications, and other things like that. The incidental benefit out of this is that you get the same performance benefits that the C programmers get out of doing it manually to their program. And so, often if you're traversing your data structure, you have smaller working sets, you improve the spatial locality. Something that we find is for linked lists, often what happens is the linked list is now laid out sequentially in memory instead of scattered throughout it. And Harvard prefetchers like that a lot. So you can get some performance out of this. So I'm just going to talk about the algorithm from a high level again. The basic idea is that for now we'll just assume that each node in the graph gets a separate pool. The pools will be mostly type homogeneous, we think, and we want to retain the explicit freeze from the objects. So you can allocate memory out of a pool and then explicitly free it back. And we're retaining the C semantics, so you don't get the explosion of memory kinds of things that would be bad. So here's our example. This should look familiar. Basic idea is really simple. We just want to put these two things in different pools. Here's another example. We just want to put them all in different pools, and this kind of makes sense. So let's take a look at what the transformation actually does, and I'll explain a little bit of how it works along the way. This is our example from before with one minor detail. Here we have this guy up here, which is some global variable, which is going to point to this list. Okay, so because of that, the two objects are different. One is local to the function, one isn't. The free list function, we don't know that it frees all of the memory objects allocated from the make list object. And so because this function could escape out, we have to handle it differently. So first thing we want to do is we want to look at this X list, right? We want to stick it in a pool. We analyze the function, and we do basically an escape analysis for the whole data structure. In this case, it's one node, but we do escape analysis for the data structure and find out that the lifetime of this data structure is bounded by the function toList. Okay. Because of that, we can create a pool descriptor to hold to describe the pool, initialize it on entry of the function, destroy it on exit. So the pool destroy will free all the memory for the pool, regardless of whether it's actually free, has all been deallocated or not. And then anything that needs to allocate or free memory needs to have that pool descriptor around. And so we look at the data structure graphs, and the data structure graphs tell us that this function references or allocates or frees memory, and so it gets passed into there and to there. Then we hack on this function and add a pool pointer, and instead of calling malloc, we call poolalloc. It's recursive, so we pass it back in. This makes sense. This is pretty simple. For this one, it's a little bit more difficult because the lifetime of the pool isn't bounded by this function. And so what we do is we actually pass it in from outside. And so when we're processing this function, we can see that it escapes out. And so that means that a caller will have to allocate the pool descriptor and pass it to us. And so this means that we get the pool descriptor, we pass it in the same places. Pretty straightforward. Now the implications of this are that the caller will at some point allocate the pool descriptor. And since this is a global variable, this thing will escape all the way out to main, which means that a lot of arguments will be added to the functions of the program, which is bad. I talked about this. I don't want to talk about that. So basically it's a simple problem, it's a simple solution. Instead of passing the pool descriptors down through all the functions, you just make the pool descriptor itself a global variable, initialize it on entry to main, and then in every function that needs to reference it, you just use the pool descriptor. It's pretty simple. You can do other things. So for example, because the pool destroy deallocates all the memory from the pool, often you have loops where you create the data structure, you use it, and then you destroy it all. And so you can just delete the destroyed all loop, which can save you a whole traversal of your data structure, things like that. We haven't implemented these yet, but it shouldn't be super hard. The more interesting thing is that segregating pools based on their connectivity patterns is not always a good idea. And so, you take a relatively simple multi-level data structure like this. If the hot path through this data structure is this edge, for example, you want this pool to be separate from these two. However, if this is a hot edge, if you go down one link in the tree, one link in the list, and then dereference this pointer every time, it doesn't make sense to put these in two different pools of memory because you're hurting locality instead of helping it. And so there's a whole ton of work that you can do with looking at coupling profile information on the data structure graphs or figuring out heuristics for co-locating memory objects, different ways to be smarter. Now, in a lot of cases, you'll lose some type homogeneity of the pools, right? Because if you coalesce this pool with this pool, you'll have objects of both types. So in some cases, you don't want to do that for some follow-on transformations. But in general, it's not a bad idea if you're just going for locality. The pool library can handle mixed stuff. So, how does this work? Here are some programs. These probably look somewhat familiar. Mostly the same things. We have like the Olden benchmarks and the pointer disk benchmarks and most of the spec benchmarks. So sizes, number of static pools, and so you can see that some programs have a fair number of static pools. The simple programs like Triad or the trivial little Olden programs don't really do much. They have one data structure and that's it. So they aren't really helped or hindered by this kind of thing. Again, we see that type safety is pretty prominent. So out of these pools, most of the pools are type safe, or homogeneous also, type safe and homogeneous. Dynamically, we can see that the number of pools created in the simple cases is exactly the same number as the static pools. In other cases, it's very different. It just depends on the behavior of the program. If they're creating temporary data structures or not, then that's where that comes from. And we can see the number of arguments added to the program, and it's not obscene. Yeah?
I've still not been able to figure out how does type homogeneity relate to physical locality of objects.
You're right. I confused two issues there. So locality is something that is a property of the pool overall. And so if you coalesce two DS nodes into one pool, you can get better locality from that. Now you can lose type homogeneity. They could be different types of objects.
What would be the advantage of having completely type homogeneous?
Okay, so something that I don't really talk about in this talk, and I could, but probably not, is that the pool allocation is just the first step. So you can do lots of transformations later that can use the properties of this transformation. A simple example is a transformation we call pointer compression. And so the idea is that on a 64-bit system, each pointer is 64 bits, strangely enough. Those use a lot of memory and cache and space, memory bus bandwidth, all this stuff. And in a lot of cases, a program compiled for 64 bits runs slower than for 32 bits, right? This is a problem. Okay. So in some cases, it's really easy to solve that. In other cases, it's more challenging. For recursive data structures, what you can do is if you're type homogeneous and if you have pool allocated the thing, instead of storing pointers between all the nodes, you can actually replace those with integer indexes into the pool. And so instead of storing a pointer to some node in memory, you just say, oh yeah, that's 54. And the nice thing about that is that you can choose to compress it as much as you want. And so if you have, if you compress it to 32 bits, you're probably fine. I mean, you can hold 4 billion objects, which is going to be some number of large bytes. Most programs won't overflow that. You could also compress down to 16 bits. Now, most programs will overflow that, so there's a problem there. But because you know exactly where the objects are in memory, and because you know the type information, you could have the program dynamically, at runtime, go in and rewrite its data structure. The compiler can insert the code to do this. And so at runtime, you're allocating. Oh, whoops, I allocated the 2 to the 16th node. I don't have an index for you. What do? Well, it can go in and rewrite the pool and switch to a different code path that's using 32-bit indexes, that kind of stuff. And so for that, you want homogeneous pools. For locality, it's not a big deal. It doesn't really matter at all. But the following kind of stuff, it can or it might or it might not be important. So we've done some safety work with this, and the safety work also requires type homogeneous pools for memory safety for programs. Dinakar would be a better person to talk to about that than me. He's the expert. But there's different applications. So if you're looking at the numbers, you might wonder what this silly B thing is 197 parser. Before I talked about custom memory allocators and how horrible they are for data structure analysis and how horrible they are for static analysis in general. 197 parser is nice because it's custom memory allocators in a separate file, and it actually works like malloc and free. And so as an experiment, I just hacked it out and changed its xmalloc just calls malloc and its xfree just calls free. And when you do that, lines of code drop by however much the allocator was, but suddenly the analysis is able to actually do stuff. And it's able to actually identify data structures. It's able to actually do interesting things, where before it just said, oh yeah, there's one node in the program, and all heap objects are allocated out of that one node. And if you pool allocate with that, what you're basically doing is you're replacing the system allocator, the system heap, with the pool library, which, I don't know, I mean, my pool library isn't as optimized as the system heap, so that's not a good idea. Here's some simple speedups. These are I wouldn't put too much faith into these because these aren't tuned at all. This is basically taking everything that could possibly be pool allocated and pool allocating into their own different pools. So this isn't doing any smart coalescing with pools. This isn't saying, oh look, you allocate an object and then free it. I won't make a pool for that. This is doing anything that's allocated out of the heap now gets their own pools and are allocated and freed from that. So given refinement, these could be better. What you find out is that most programs aren't affected. So especially spec benchmarks, they don't really care about recursive data structures in large part, and so you don't really see it at all. Because my pool allocator isn't wonderful or fancy, it can't compete with the system heap. And so if you're allocating and freeing everything out of that instead of using malloc, I'm not going to be able to do anything for you. There's no value add. And so the basic solution for that is that you say, oh look, I'm not going to be able to do anything useful, so I just won't do the transformation. And you can choose to do that on a per node basis. Other programs speed up in reasonable ways. So these are some pointer intensive programs. You get 30-40% speed ups. A large part of that is cache misses that are reduced. In parser B, you get a 24% speed up. And so what this table doesn't show you is that, so in 197 parser, they actually wrote the custom memory allocator for performance. Right? We ripped that out and replaced it with malloc free, and if you run the modified version of parser, it runs slower than their tuned version. Okay, well that makes sense. We speed up the modified version by 24%, and that basically gets us to within 3 or 4% of the custom allocator version. And so, though we took out all the custom tuned memory allocator, the domain-specific allocator for that program, we're able to get most of that performance back with a generic compiler transformation, which is nice. And it's a compiler transformation that you could use for other follow-on work, because locality isn't the be-all and end-all of everything. So
When did you run this on? What is the cache and memory size?
This is a Pentium 4 Xeon.
What's the cache size?
Probably a megabyte of, I don't know. It probably has a 512 L2 cache and 2 megabyte L3. I don't really know. It's a P4 Xeon 3.0.
What is the ref inputs for the spec?
What's that?
Have you used the ref inputs for the spec?
This was train inputs, actually. So these ran 10 to 20 seconds or something, so enough for them to not be completely noisy. So if you take a look at the ones that are actually being helped, strangely enough, it's due to cache misses. And so this is measuring the cache miss reduction using perf counter, and you see that on pointer intensive programs, the cache misses go down. And so the left-hand side is the miss rate reduction, and so 100% reduction would be it now has no cache misses. That would be nice, but didn't happen. On one program, FT, you can see that we reduced the L1 cache misses by a whole bunch and then found some new L2 cache misses. And it's still sped up by quite a bit, I guess. So 34%. So I guess that's just fitting more densely into the cache.
So the absolute miss rates for all these programs are pretty small, right?
I don't have the absolute numbers. I mean, they're like millions of, I don't know how to calibrate that compared to anything. But yeah, so, I mean, we're seeing a 68% reduction in miss rate, but that doesn't correspond to a 68% speed up.
Right.
So, I mean, this is, if you're looking at locality, the speed ups are the more interesting one, I think. But you're right, if it's not missing in the first place, it doesn't really matter that much. So yeah, highlights. So basically, if you use this transformation as a locality thing, then you can, we're just taking data structures, we're transforming them, and changing them to use a runtime library. And we're giving compiler control and enabling subsequent optimizations and analyses and things. Basically, the thing that I find interesting about this myself is that you're basically combining two different things. You're combining static analysis and static, information about the program with the runtime control and the runtime information about the data structures. And there's tons of different applications for this kind of stuff. Even you can use this for garbage collection, region-based garbage collection stuff. You could use this. It seems like there's a lot of different things you could do for data structures. And one of the things that's interesting to point out about this is that this is a compiler transformation, and as such, if you do it wrong, it breaks your program. And so, in particular, if you analyze the program wrong and you deallocate your pool too soon, well, you've just freed all the memory that the program's using. And that's one of the things that differentiates it from earlier work on heuristic-based locality stuff. But I think that's important because it gives more information to the compiler. So, how are people feeling? Yeah, why don't I just do this? So, yeah, you can do some stuff with architectures and, yeah, okay. So, if you're interested in processor design, talk to me. So, basic story of the talk is this LLVM thing. It's a low-level representation. Being low-level is good because it means that you can, the analysis, the transformation is all very simple. People can understand it. People understand how to use it. You can, convert between text and binary really easily. There are advantages to that. It's really efficient to JIT, for example, stuff like that. It also has the high-level information you need to do crazy things like rearranging data structures and hacking on programs and high-level types of things. And as pointed out, there's a lot of information we don't have. And so it's not the one true solution for all the ills of computing or anything like that. But it does have a lot of good applications, I think. So the macroscopic stuff is looking at data structures from the holistic perspective. Can I take a data structure? Can I rearrange it? Can I jumble it around? Can I do this to a potentially type-unsafe C program, which is kind of difficult to deal with in a lot of cases? Or rather, can I do it without breaking some, which is the important part? And then, that kind of stuff. Stuff I didn't talk about is, how to make processors faster, which, as long as they get faster, nobody cares. So, is there any questions?
I use functional languages a lot.
Yeah.
If you're writing OCaml or you're writing SML, all you do is you allocate linked lists. Yeah. And it looked like all of those benchmarks were for C code or C++ code.
Yeah.
Have you tried benchmarks with functional languages?
Have not tried that. I suspect that so one of the reasons why I'm here is that I'm looking at applying some of these techniques to MSIL programs. And so the first project I've been working on is converting MSIL to LLVM. Because MSIL programs, like functional programs, allocate a lot more freely than C programs. In a lot of ways, C programs go out of their way to do anything possible to avoid hitting the heap. That's annoying if you're looking for test cases. We don't have functional language front ends functional yet. Okay, well, yeah, they're not ready yet. So I can't really apply to that. Now, if they're compiling to LLVM, this works on anything that can be compiled to LLVM, and we have mappings in our little brains of how compiling OCaml and Scheme and stuff would work, and so we don't see any problems with that. Like I said, I suspect that the speedups and the improvements and stuff would be more impressive than this.
Most or list-based runtimes, they have different optimization techniques than the techniques that you have now in imperative languages. So they most probably are doing lots of good stuff for you as far as allocation or de-allocation, etc. is concerned.
But you are dealing with lots of linked lists, and if you have immutable linked lists as part of the language, then you're going to use them heavily. And even though you have deforestation and lots of other, domain-specific optimizations going on, the memory is still important. I don't know. And yeah. So, anything else? Okay.
Thank you, Chris.